Yes, today's class is Thermodynamics, higher secondary first year, and it is the continuation of class number 32. In the previous class, I have already mentioned spontaneous process, and today the very important topic is entropy and Gibbs free energy and spontaneity. Spontaneity of a reaction or spontaneity of a process. So, before defining entropy, Gibbs free energy, and spontaneity of a system or spontaneity of a process, let us define some of the important factors to make the topic more interesting and understandable. So, first of all, spontaneity. So, before starting that very interesting topic, entropy gives free energy and spontaneity of a system. Let us define, which we have already defined in our lecture number 32. What is spontaneous process? The process which occurs by itself without being any work done on the system is called spontaneous process. All the natural processes are spontaneous, where no amount of no external work is to be done on the system to make the process to proceed. So what is del H will get in defining the spontaneity of a system. What is del H? It is the total heat content of the system. Del H is maybe positive, del H may be negative. If it is positive, it is called endothermic, and if it is uh, del H is negative, it is exothermic. So this concept of exo and endo is already known to you. If heat is absorbed in the system for a reaction to proceed, then it is endothermic, and if heat is evolved out after getting the product, then it is called exothermic reaction. I don't want to spend much time on the definition of endo and exo. So del H is this. What is entropy? Entropy already I have defined. Entropy is the measure of the disorderliness of the systems or the randomness of the molecules in a system. It is the measure. So the entropy we will define mathematically equal to Q by T or dQ by dt. We have already done in the previous class. Now what is del G? And this is the main topic of today's class, is del G. Del G, it is the amount of energy available in the system for doing valuable work, for doing valuable work. So for roughly, let me define this. It is the energy. Del G is nothing but energy. It is Gibbs free energy. Del G is the amount of energy available in the system. In the system, that amount of the energy should be available in free mode to do some valuable work. So free energy which is required to do some valuable work is called Gibbs free energy. Now how it is free and how it is available? That amount of energy is available and it should be free to do some valuable work is called Gibbs free energy. Let me give some examples. In the cell, you have galvanic cell, or if in the cell you have seen that one is uh, anode and other is a cathode, and there are some solutions. Some solution is there, and some ions moves towards cathode, and some anodes electrons are going to be exchanged in the reactions, and the mechanism there is flow of the electron in this way. So if I ask you, then electrons are moving, one is cathode, other is anode, one from anode to cathode, or anode to the solution, or solution to cathode, solution to anode. Am I right? There is a movement of the systems, and due to which there is a difference of potential in the cell. Am I right? Simple Boltzmann cell, or whatever cell we have explained already in other classes. So if I ask you what is the driving force which makes this movement of the ion from one end to the other end, which creates some potentials in between the two end, and that creates current, what is the source of the energy, where that energy comes out? This energy which are available in free to make the ions movable from one end to the another end is called free energy, available already in the systems. You need not to require supply the energy in the system. It itself arises in the system, is free in nature, and that amount of energy is called Gibbs free energy. Am I right? So next, at the very second, I want to tell that is third law. Third law, entropy of all the perfectly crystalline solids is zero at absolute zero temperature. When temperature of a perfectly crystalline substance is taken as 0 degree, then the movement of the gas molecule restricted in such a way there is no randomness, and it becomes zero at zero temperature, and this is called third law of thermodynamics. Now, so our main point of today's discussion is the spontaneity of process or spontaneity of a reaction. So how will define the spontaneity, whether reaction is spontaneous? We have seen that if entropy change is greater than zero, it is spontaneous. The process is spontaneous. And today we will see if it is less than zero, if del G is gives free energy is less than zero, it is spontaneous. For time being, you keep it in your mind. Am I right? Now we will define the spontaneity of a system, spontaneity of a process. Today we will define it. How we will find out the criteria. So entropy and enthalpy. This is enthalpy. Alone cannot. Very simple process. The change of entropy or change of enthalpy, maybe del S positive, del S negative, del H positive, del H negative, we have already defined a bit earlier. And alone entropy and alone enthalpy change is not the sole criteria, is not be the sole criteria, only criteria as well as sole criteria for spontaneity of a system. You cannot define the spontaneity of a process or the systems or the chemical reaction, whether it is a spontaneous or not, simply by defining entropy or simply by understanding del S, del H of the system. Solely these two terms alone cannot define the spontaneity of a process. Now, the spontaneity of a process can be defined, can be found, can be meaningful, can be detected, can be predicted only when both these two terms combinedly give some idea, then we can find out del G. Am I right? So, to find out the spontaneity of a process in terms of gives free energy, then we need both the term to come together. So we know this is a relation where gives free energy I have already defined. It is a available energy free, available energy in the system for a valuable work to be done. For a valuable work to occur in the system, some amount of available free energy is required in the system. Energy, if free, should be supplied in the system, should already be in the system, uh, is called gives free energy. This is called gives gives Helmholtz equation. Just to keep it in your mind, G is equal to H minus T del S, where G is equal to gives free energy, H equal to enthalpy, T is the temperature, S equal to entropy. So a bit earlier we have told you that enthalpy and entropy alone or sole cannot be criteria of spontaneity of a reaction. For the reaction to define the reaction whether spontaneous or non-spontaneous, we commonly know this H and S, and this combination of this term enthalpy and entropy can be calculated from Gibbs Helmholtz equation is given by G is equal to H minus Ts. On integrating this, del G is equal to so what you write, del G is equal to del H plus, just we are differentiating this, del G is equal to del H minus del Ts, and in del Ts may be written as S del T plus T to del S. That S is constant and T is variable. T is constant, entropy is variable, but we know the system is here at constant temperature. Del G is always at constant temperature, so at constant temperature, so change of temperature T1 T2 is equal to 0, so S del T is equal to 0 means there is no change in temperature is equal to 0. So if you put here 0, S into 0 equal to 0, so S del T becomes 0. So we are getting del G is equal to del H minus T del S. Total equal to del S system plus del S surrounding. It is 2. It is known to us in earlier classes. I have told you then del S total is equal to del S system plus del S surrounding. Del S entropy of the change of entropy of the system plus change of entropy of the surrounding is equal to change of entropy of total means inverse. So this is this. But if you assume entropy of system surrounding is increasing, that is entropy of system is decreasing at equilibrium. Just at this point you fundamentally follow, if we assume the entropy of system, entropy of the surrounding, entropy of this surrounding is increasing. This is system, and out of this system everything is surrounding. We see if the entropy of this surrounding is increasing, means it is at the cost of the system. So some amount of energy is being transformed from the system to the surrounding. Hence the entropy of the surrounding is increasing at the cost of the increase of the entropy of the surrounding. Entropy of the system is decreasing at equilibrium. When the system is in equilibrium, so the energy flow will start from system to the surrounding. Am I right? So if one system entropy of the system is increasing, entropy of surrounding is decreasing. If the entropy of the surrounding is increasing, entropy of the system is decreasing. So if you assume entropy of the surrounding is increasing, that is entropy of the system is decreasing. So if entropy of the system is that is del S surrounding so if the entropy of the surrounding is decreased, that is entropy may be written as entropy is equal to q by t or dq by dt, or we may write in terms of h, in terms of enthalpy we can write change in enthalpy by t. Though if you assume entropy of the surrounding is minus dq by dt, then entropy of the system is plus dq by entropy of the system is positive. So entropy of the system, what to write, entropy total is equal to entropy of system plus entropy of surrounding. If you assume it as this, so in equilibrium, if one is increased, other is decreased. This is entropy of the system and this is entropy of the surrounding. If we assume entropy of surrounding is minus, then entropy of the system is plus. So if this is in entropy, so del S may be written as del H by T, because it is Q by T, entropy is equal to Q by T, we can write entropy is equal to del H by T. If del H is equal to negative, so we can write entropy of the system is equal to plus, you can write here plus and you can give it here minus. Same thing means system is minus, surrounding is minus, system is plus. So this is entropy. So if you all through multiply it by T, so what you get here, T into del ST is equal to very simple, multiplying all through by T, we get T del ST plus T del S system minus TT cancel is equal to this. We know for spontaneous process, a bit earlier I told you del S must be greater than 0. It is known to you in earlier classes, that is randomness of the universe process is always increasing, entropy is increasing, it is a spontaneous process. So for spontaneous process, entropy always must be greater than 0. So if del S is greater than 0, then T del S also greater than 0. Therefore T into del S is also greater than 0. Then this term must be greater than 0. That is greater than 0. This is greater than 0. Then this term T del system minus del H, or so we can just arrange it in this way. So we have seen del G is equal to, just I am showing you from here, from these two we have got del G is greater than minus del H minus T del H system. Am I right? So this is equal to you see del H minus T del S, del H minus T del S equal to del G. Am I right? So from A You write from A, make it A, this is del G minus del G, that is del G less than 0. For del G negative, entropy, a system is spontaneous. So from this, what we see, that is del G is less than 0, means the value of del G is equal to 0. What we assumed here, the system in terms of entropy is spontaneous. So for a process to be continuous, so del G must be less than 0, means del B should be negative. So for the term spontaneity, what we get, del G is equal to minus something, that is if del S equal to 0 less than 0 is greater than 0 is spontaneous. Now we have got del G less than 0, it is spontaneous. We have arrived these two criteria, one is del G and del S. Let us write the equation, Helmholtz equation. Del G is equal to del H minus T del S, where del G equal to Gibbs free energy change and del H equal to enthalpy change, and T is the temperature and del S equal to entropy change. Am I right? So let us consider for endothermic reaction, and we know that del H for endothermic reaction is greater than 0, and del H means change of temperature for the reactant to the product, that is final product, is not high, it is low. So what you see from here, this part is greater than 0, it is greater than 0, del H is greater for endothermic reaction, del H is greater than 0, and its value is not high, its value is low. That positive value is not high, very low. So if the positive value is not high, very low, what does it means? If you assume the temperature, very low temperature, very low temperature, this is 0 no doubt, but that value is greater than 0 no doubt, positive no doubt, 5 6 7 like this, but very close to positive, very lower value, not high, then the whole value of G depends upon this. Now to if it is positive and value is low for endothermic reaction, then at very low temperature, if the temperature is very low, then at this low temperature, the entropy means randomness will also be very low. So low into low again will be low. So that product of this low temperature value and entropy may not cross this positive value. So it is 5, and this product has certainly crossed to 3.4 something, because value is low and entropy is also low. It has not crossed this low positive value because temperature is very low. At very low temperature, entropy change means randomness is very low. Product of this temperature again low. So low minus again very low of this is positive. So you are getting that is positive, means at very low temperature del G is positive, means it is non-spontaneous. So it is one of the criteria for endothermic reaction. Del H is positive, greater than 0, positive, and del H value is very low. Am I right? So if you assume the temperature very low temperature, then the product of T and entropy is also less. So less minus this less again is positive. The whole term is coming out as positive. So del is positive. If del is positive, answer is non-spontaneous. So del G is positive means non-spontaneous at very low T. At very low T. Am I right? So one process is over. Let us assume very high temperature. Very high temperature. Minutely follow. If you don't know the technique or the fact, you cannot answer any questions answer. Very high temperature, what's happened? For endothermic reaction, we know del G is greater than 0, no doubt, but its value is not too much high. Now, what we are doing here is the temperature is too much high. If temperature is too much high, randomness is change of entropy is also high. So the product of these two is going to be higher and higher and higher. So the low value minus higher, we are getting what? We are getting negative value. So del G is equal to negative, means it is spontaneous at temperature is very high. Temperature is very high for endothermic reaction. Am I right? So for moderate temperature, if it is moderate temperature, not high, not too low. So you give this to minus, it will be a bit higher than this one. This will be a bit higher. This one, this will be negative. The reaction, the process again will be spontaneous at moderate temperature. Now, endothermic process is over. Now we will proceed to exothermic process, where del H is less than 0 and del H is extensively high. It's high enough. So what we get here is that for exothermic reaction, del H is less than 0 means itself is what? Negative value. So whatever temperature you use here, either low or moderate or very high, the answer itself again is minus. So both this minus will give you minus. So for exothermic reaction at any temperature, the del G is negative. So del G is negative means spontaneous at all temperature if the reaction is exothermic reaction. So these are the some criteria with the help of which we can tell whether entropy, or with the help of the value of del S, del H and temperature, del S, del G, del H and temperature, we can predict whether a process is or the reaction is spontaneous or non-spontaneous, fast or slow, or feasible or not feasible. If it is spontaneous means feasible, if it is non-spontaneous it is non-feasible. Thanks a lot for watching the class. Hope I have understood the class with utmost interest. In my next class I will again start with new recent more exciting topic. Please don't forget to subscribe the class to remain updated.